Okay, so we've been exploring the particle in the one-dimensional prison, so it's forced to live between 0 and L, between x equals 0 and x equals L, and we've concluded that the functions, the spatial parts, in this case, they are a function of x, has some coefficient times the sine of k times x, where the boundary condition KL, the boundary condition at x equals L, gives us k equals n pi over L, where of course k is equal to 2m times the energy over h bar squared. And so our energies, as we've shown, are now, we can now write them in terms of this n parameter, pi squared h bar squared over 2ml squared. So, so the lowest value of the energy is pi squared h bar squared over 2ml squared. E2 has n squared equals 4, so that's 4 times the value E1. E3 has a value which is 9 times E1, and so on. E4 has 16 times E1, and so on. Right, so not any value for the energy is acceptable. They come in discrete values. So let's look at this function, psi n of x. These are the eigenfunctions of the system. So we could say maybe that there's an an sine of n pi x over L. And let's plot these. So when n is equal to 1, we have the sine of pi x over L, and this is just a function that goes to 0 at 0 and L. So it's something like that. Let's plot the function with the next energy level, so that would be sine of 2 pi x over L. Let's see what the spatial function looks like. So this is L, this is 0, and this function at L over 2 is 2 pi. It gives the same value that this function gives at x equals L, so it must go to 0 at L over 2. So we've just created 2 bumps. And if we do the next energy level, we'll start to see the pattern here. This would be 3 pi x over L. Then at x equals L over 3, we have that this is equal to pi in here, and so that's where it goes to 0 the next time. So it goes to 0 here, but also at L over 3, and then at 2L over 3. So initially we divided it into 2 parts. Now we're going to divide it into 3 parts, so the function goes to 0, well, not a great, something like that. It goes to 0 there, and then it goes to 0 again at L. And of course, we can continue doing this when we do the next energy level. We have 4 pi x over L, and we're going to divide this by 4. So this will be L over 4. This will be L over 2 and 3L over 4. So this is 0 L over 4. This is L over 2, and this is 3L over 4. And the function does that. And so on. So we're starting to see that as the energy increases, we get more waves or more nodes. And so we want to get a sense of what this number is here. Let's see what that is. Of course, the normalization condition will get us this value, but let's try to get it without doing any integration. So here is the sine function that we see here, which goes to 0 at x equals L. Of course, we need to consider the modulus squared. We want to integrate this kind of a function, and so it's going to be a little bit different from this because we're squaring it, but that will give us the total area under the curve, and the integral of that would have to be equal to 1. But if we do the same thing for the function, so this is sine, this is pi x over L, or sine squared. Let's consider sine of 2 pi x over L squared. Right, so that's just going to be this quantity squared, so it's basically, if this is L, then we get a bump in both places here. Maybe not the best drawing. And then the area under the curve will be this area plus this area. And this is L over 2. So for here, we can say that if we call, let's write this A1. So this is A1 modulus squared, and then here we would have A2 modulus squared. So A1, sorry, let's write the area here, so area, let's say area 1, here, this is going to be if we just consider the part with the sign, that has to be no greater than 1, and we're integrating to L, and so clearly this has to be L over, has to be some, if we just forget A1 for the time being, then this has to be L times 1 at most, so it has to be less than L times 1. So it's really L over C, where C is some number greater than 1. And the total area here, let's call it area 2. So let's call this is area 1, and let's call this area 2. The area 2, this function here, is exactly like this function. So it would be L over 2C, but we have 2 of them. So the total area here would be 2 times area 2, which is L over C. And so the point is that this total area is the same as the total area here, and we can continue doing this for higher values of n. And so the point here is that it doesn't matter what the coefficient A1 is. So the integral from 0 to L of the sine of n pi x over L in dx is equal to, it turns out C is equal to 2, and so we get L over 2, regardless of what n is. So it's independent of L. And so when we bring in the a's, they're all the same. It's just one a. we'll do A modulo squared times L over 2. This has to equal to 1. And so we get that the modulus of A is equal to the square root of 2 over L for all of our eigenfunctions.